Okay. All right. Now it really is. All right. Well, sorry for
Linux
late.
is better.
What?
Linux is better.
Yeah.
To each his own. I
Well,
don't
we're all
insult
better than
anyone.
Windows, so apologies to any Windows aficionados, but
Yeah, well.
I remember I was around before Windows and everything seemed
I
fine
mean, I
then.
have Windows on my Mac.
That's just really weird.
Yeah, I'm set in my ways.
Okay. Have all the operating systems. Okay. All right. Well, sorry for a late start, but we'll still finish on time. So, okay. Well, we still might have one or two more who are coming. For the most recent quiz, well, I just put up. We're getting into a new chapter today, section 5.1. I put up a quiz for that. The last quiz in chapter 3, I struck a question from it, question 5, because although it was something that we had talked about in class, it's very important that the concept check questions, the answer should be one should be able to find them from the reading, and as opposed to something that is actually the answer to a exploration. So there's a freebie for you. Well, no one had lost points on that one yet anyway, because also not many people have taken the quiz. I'm getting ahead of myself putting up the assignments just so you know what's coming. So we have homework 3 that's due on Tuesday, and then the 20th, and then the following Tuesday will be homework 4, which will be based on this material. I'm not sure if I'll get through all of this today. That's the plan, but I'm not going to be broken up about it if I don't. It'll be fine to continue that on Tuesday. Okay, and I really am not going to bother asking you guys if you have any questions on homework, because you're just going to sit there and be like, mm. So.
Well, I had one, but it was answered when I looked at the hints page. So.
Oh yes, good thing you mentioned that. I just put up this morning hints for homework 3, and homework 2. I know I need to grade that. I will try to get on that soon, like maybe over a weekend or something. So
Grading is overrated.
Well, yes, because it's just the worst part of the job, pure and simple. And I think that's why we have such a booming business with online homework. And I love not having to grade a dang thing for my other class, 102 online. Okay, so you might have thought that we were done with AX equals B from getting through a chapter, but no, we're actually going to spend a little bit more time on it. And besides solving systems of linear equations, there's not just a lot to study there for its own sake, but in the context of solving other problems, like what we'll see later on, like certain differential equations, we will also need to solve linear systems. So it's one of those fundamental problems in numerical analysis that just keeps coming up. So what we've seen so far is category of methods for solving AX equals B known as direct methods. And by that, I mean Gaussian elimination, coupled with substitution. And any variations thereof. So from what I've been talking about more recently, like what would be one variation of Gaussian elimination that we talked about?
Pivoting.
Well, that's really okay. That's still under Gaussian elimination because it's something you modify to it, but a whole separate approach. What? The LU decomposition is what's produced by Gaussian elimination, so really they're the same thing from different perspectives. What? Sorry, what? Yeah, which is probably what you were going to say also.
Yeah.
Yeah.
The Tredeschi, and we also have the tridiagonal stuff that
of abandoned stuff. So that's which then what you're doing in that case is you are optimizing Gaussian elimination to take advantage of that nice structure. And then, but if you have a symmetric positive definite matrix, you would not do Gaussian elimination at all, even though you could about pivoting. Cholesky factorization is what you could use instead. Also, or there's also LDLT that's closely related to that. Okay, so all of those methods, everything we've seen so far is under the umbrella of direct methods. So, so I think, okay, we have this catalog of methods that we can use for solving whatever system of linear equations that comes along. But now I'm going to explain to you why we're moving on from them. We are breaking up with them. Why direct methods are bad. Now, not entirely bad. They still have an important role, and coming up with better direct methods is still an active area of research. So they'll always be part of the picture. It's just that for certain situations of importance, situations that come up very often in real-world applications, these are an absolutely terrible choice. So not to suggest that covering all that was a waste of time, and also certain elements of direct methods do play a role in the alternatives that we're going to see. It's just that we need to step back and rethink, and a lot of it has to do with the reality of solving these kind of important linear systems on a computer. That changes things compared to back in like pre-World War II when it was people working for the Department of Agriculture were solving systems of linear equations. They would sit at a desk all day and do Gaussian elimination or something like that. That must have been really awful. And they were called computers. That was their job title. What do you do for a living? I'm a computer. Good times. So, okay. So one reason why we no longer like direct methods, why they're on our blank list, is I don't know what I'm thinking. I have sworn on YouTube, so. Okay, what if we already have an approximate solution? In other words, some sort of initial guess, something that already is in the ballpark. So like AX is almost equal to B. And the problem is, there's absolutely nothing in how direct methods are set up to take advantage of that information. Can't write today. I guess I can't write any day, but it's particularly bad today. So that information that in many applications, such as differential equations, that we will have on hand, Gaussian elimination would be like, yeah, so what? So Gaussian elimination says, I work alone. So it doesn't play well with others. Okay. So that's just one problem. I actually have 4. Hopefully I'll remember all of them. Okay. Second problem is what if we don't need very high accuracy? Now, it seems like a strange thing to ask. You might think, well, don't we always want all the accuracy we can get our hands on? No, because sometimes in whatever problem you're solving, so wherever your system of linear equations comes from, you have uncertainty. It's a mathematical model, there's uncertainty in the model. Like, for instance, in my former life in petroleum engineering, we're solving differential equations. The coefficients come from geostatisticians, and they're giving us a fuzzy picture of things, because that's all they can do. So there's no point in expending a lot of effort to get high accuracy for a problem in which there's already a ton of error. Low accuracy would be just fine. So you might think, I would rather devote less time to get a somewhat accurate solution than spend a lot more time to get a highly accurate solution. But the thing is, Gauss elimination again says it doesn't care that it's going to solve this problem exactly, except for rounding error. So direct methods have no way of, I guess the best way to put it is, they can't stop early. A lot of methods we'll see, I mean, like when you have iterative methods, the idea is you keep iterating, you prove your solution each time, and you decide when it stops, when you have a certain level of accuracy. And we make that choice. Direct methods don't give us that choice. We're going to go. You have to let them run to completion, and they're expensive. Order n cubed operations. Okay, now, as if that wasn't bad enough, I have more. Well, this problem has already somewhat been mentioned in the context of banded matrices. What if the matrix A is sparse? In other words, most of the entries are 0. Well, then you perform row operations on that. Now, by sparse, I mean not necessarily banded. And that's an important category of matrices, but there are a lot of problems that come up where the matrix is sparse and not banded. The entries seem to be randomly scattered through a matrix. You perform row operations on a matrix like that, and you're going to introduce a lot of new non-zero entries that weren't there before. And from our discussion of banded matrices, does anyone remember what that phenomenon is called? Yes, great. It's fill-in. As mentioned with banded matrices, but really any sparse matrix, it can be a problem. So we'd like to avoid that. So any alternative approach would be welcome. So now that iterative methods are pretty down low, I'll kick them one more time. So what if we don't actually have A to begin with? Which sounds like a strange question. It's like, how do you expect to solve a system of equations AX equals B when you don't know what A is? Now, I have to explain that. In other words, we don't have A in terms of its individual entries Aij. So instead, you have something like this. Y is equal to A times X, but it's represented by a function. So you have some function, like a MATLAB function, where the input is X, and the output is A times X. So you don't have the individual entries Aij for ij equal 1 to n. Now, you could get them, like if you went ahead and called this function with every column of identity being for x, then you would have A. But that's a lot of work. You don't want to do that. So, but Gaussian elimination requires having each individual entry Aij, and then you keep updating them. So if we could find an iterative, any kind of method that will work with this black box formulation of A, where an input vector x goes in, and then the output Ax comes out, that would be ideal. So a method that's based on matrix vector multiplication instead of row operations would get around this issue, and maybe could get around these other issues too. All right. Okay. So I'm seeing. Before I move on from this board, is there anything here that I've written so horribly that it can't be read? Like I can see you like craning your neck and so forth. It's like, okay. And again, it's all in the book too. So, first page of chapter 5. Okay, so this has us looking for a completely different approach. We just scrap almost everything that we've seen before. So now I'm going to explain what do we mean by an iterative method, and the different categories of iterative methods. Well, there's just two, and I probably will only be able to spend time on one of them. Okay. So now we're getting way past the kind of things that you would ever see in 326. So this is where the real linear algebra is done. Make sure it doesn't fall. Okay. So actually, iteration is going to be a very important theme for the whole rest of the course. For now, we're going to talk about them for linear systems, but later on we'll get to nonlinear equations, and we'll use them for that too. And there'll be some similarities between the two. Notice I'm 20 minutes in, I've not boxed anything yet. Yeah.
You got a lot of lines though. Lines are
Okay. Okay.
We have our own conversations.
Yeah. Okay. Okay.
Should box in the word instead. It's important.
What?
Box in the word instead.
Oh. No, that's too bad. Here. You want a box? You have a box. But I was going to box this anyway. All right. So there's two types of iterative methods. One's called stationary. So what you do, a stationary iterative method has this form. That each, each new iterate is equal to some function of a previous iterate. So the idea is you choose an initial guess, which I label as, I should have done this first, initial guess x superscript 0. Now, I want to make sure one thing ultra clear before I go any further. I put these superscripts in parentheses for a reason. They are not exponents. They never will be exponents. If I write x, the second iterate x2, I'm not squaring anything. So do not think these are exponents. I will not deal with exponents at all today, I'm pretty sure. So just don't go there. That may have been overkill, but I mean, I've taught multivariable calculus classes where I write partial derivative, and even late in the semester, people think those are twos. So, and if you think those are twos, then and you've taken multivariable calculus, then you forgot it all, and you should review it again. So, and this is why I write my z's like this, so that because those are my twos. Just so we're clear on the differences between these things. So, partial derivative is z and 2. Okay. Now, so that's my initial guess, often chosen to be like the 0 vector. And then we generate new iterates, x1, x2, and so on, that hopefully will converge to the exact solution x. So ideally, the limit as xk goes to infinity would be x. So the idea is, I have my initial guess, I substitute it into some function g that gives me x1, then I substitute that back in to get into g to get x2. I just keep substituting. So this is actually called successive substitution. And the reason why they're called stationary iterative methods is that the exact solution, x, satisfies this equation. X is equal to g of x. So in other words, you plug x into g, the exact same thing comes out. And we say that this is a fixed point of G, or it's also known as a stationary point. In fact, later on in the semester, when we're studying nonlinear equations, we will see this again, and the method will be called fixed point iteration. But because it's also called stationary point, these are called stationary iterative methods. And I just realized my box is too small. Okay. All right. And that's all I'm going to focus on today. So at least the methods have a relatively simple form. When you code these up in MATLAB, you're just substituting this into some sort of function, and you just keep going, and you check to see if xk is converging. Hopefully it is. It will not always. Okay. So that's one category. The other category, non-stationary. And that has a also simple but very different form, that each new iterate is equal to the previous one plus some constant factor, which I'll call alpha k, times a vector pk, and that vector is called a search direction. So the idea is, from wherever you start, you pick a direction you want to go in that you think will get you closer to a solution, and you figure out how far you want to go in that direction, so you pick a constant alpha k to multiply it by, and you just add it on. So basically you're just going through your space, like your Rn, trying different directions, and each time getting closer to the solution until you finally are close enough. I have this on the schedule to talk about non-stationary methods, but those are a lot harder to digest. Like,
Yay!
painful.
Yay!
But those of you who are graduate students, or may become graduate students in the near future, I want to make you aware that next spring I'll be teaching Math 610, which is the graduate numerical linear algebra course. It's offered every couple of years. And I will definitely talk about them there. And the last time I did, it took 3 lectures, so I do not have that kind of time. So sorry to disappoint, but if I can talk about them at all, I will. An example is if you remember any multivariable calculus at all, and some of you took that from me, so get better. We talked about the concept of steepest descent, then minus the gradient. So that leads to the method of steepest descent, where this is minus the gradient of some function. A modification of that is called the conjugate gradient method, which is definitely the most famous iterative method. In fact, it's so famous they even threw a birthday party for it. So I'm not kidding. Numerical analysts always are looking for a reason to.
Cake?
Yeah, pretty much. Who wasn't until recently the world's, in my opinion, the world's foremost living applied mathematician, but he passed away a few years ago. Joe Keller. I attended conferences for his 80th, 85th, and 90th birthday party. So they just kept on going. So, okay. So, yes, we're such hard partiers, aren't we? Us numerical people. So now we're going to delve into stationary methods, get an idea of how do we come up with one? How do we have any idea if it's actually going to work? Because that's one risk with iterative methods as opposed to direct methods. Direct methods, you're going to get a solution. You can guarantee that. It may not be very accurate, like if a matrix is ill-conditioned, there may be a lot of error involved, but you're going to get something. Iterative methods, you might not. So there's, so that's one very unfortunate outcome that we need to avoid. Okay. So I'll start with the general form of a stationary iterative method, and then we'll see a few specific examples of them. Oh. Okay, there's an eraser over there. Not that I would miss these erasers at all if they just disappeared, but although the board was a lot cleaner today.
Mm-hmm.
So you must have finally come in here and done something with it. Because this eraser's so worn down that the plastic part is scratching against the board. And it's not as bad as the fingernails and chalkboard effect, but it kind of is. All right. So, general stationary iterative methods. Okay. So what we do is we write A, we decompose A as, instead of the LU decomposition where we wrote A as a product of two matrices, we're going to write it as the difference of two matrices. A lot simpler. So, so A equals M minus N for matrices M and N that we'll have to choose. Or really, once you choose M, then that determines N. And we call this a splitting of A. Right. So now, if AX equals B, I can substitute the splitting in for A, and I get this. Okay, so M minus NX is equal to B. So I can then say MX is equal to NX plus B. So the exact solution satisfies this. And now I'm going to assume that the matrix M is non-singular. N does not have to be, only M. So now I can say that X satisfies this equation, M inverse times quantity NX plus B. Okay. So all I've done here is I've rearranged this in such a way that isolates X, but not the same as A inverse B. So this right here is how I'm going to define my function g of x for my stationary iterative methods. So that's the function I'm going to plug my old iterate into to get the new one. So, so the actual iteration is as follows. Okay, yeah, this is worth boxing. Okay. So we choose our initial guess, x naught, and I'm going to say equals 0 with a question mark. And what I mean by that is, if you don't have any particular information about the problem, like as some way of guessing a solution, then you might as well just start with x equals 0. That always works. But if you have information, like something that's already as close to a solution, then you should use it. Okay. Then, in a loop, and I'm going to say until convergence. I'll explain that in a moment. All you do is you set xk plus 1 is equal to m inverse nxk plus b. But what I really mean by that is, because we don't compute inverses explicitly, really we're going to solve this system mxk plus 1 is equal to nxk plus b. So in other words, we have an ax equals b problem where your a is now m, and then this is your right-hand side. Everything on the right-hand side of it equals that is your b vector now. And the idea is m should be chosen so that systems involving m should be easy to solve. Like maybe m is a triangular matrix or a diagonal matrix, so that you're not expending too much effort per iteration, because you're going to solve a system every iteration. And what you do is you keep computing iterates and you check, are they getting close to each other? Is the difference between them going to 0? So you stop, for instance, if the magnitude or norm of xk plus 1 minus xk is less than some chosen error tolerance, like maybe 10 to the minus 8 or something like that. And you can use any vector norm, it doesn't really matter. So all stationary iterative methods proceed like this. You choose your splitting, your m and your n, and then during each iteration you solve this simpler system, and hopefully that gets you closer to a solution. Now, but before I talk about specific choices of m and n, the big question to answer is, how do we know if this will converge? And the way we can answer that question is we'll examine the error as for each iteration, which would be xk, I'll give it a name. I'll call it ek, which is equal to your iterate, xk, minus x. So x is the exact solution. So we're just going to examine the difference between the exact and approximate solutions, and we'll see how that error changes from iteration to iteration. We need to make sure that as k goes off to infinity, that the error is going to 0. All right. So what I'll do is look at ek plus 1, so the error after k plus 1 iterations, and try to relate it to ek, the error after k iterations. It turns out there is a fairly simple relationship between them. All right, so here we'll do a little convergence analysis. Okay. Now, actually, the way I'd written xk plus 1 like by itself, that would be more convenient. So ek plus 1, which is equal to xk plus 1 minus x. Now, what I'll do is, I have a formula over there for xk plus 1, so I'm just going to put that in here. So I have m inverse nxk plus b minus x. Okay. So what I need to do now is find a way to express the right side in terms of ek. That will tell me how the error changes from one iteration to the next. And the way I'm going to do that is I'm going to replace b with ax. So now at least b is out of the picture. And then I can use the fact that a has this splitting. A is equal to m minus n. So I'll substitute that in there. I'm gonna make a confession right now. I'm just trying stuff. I don't really know where this goes, but I know what the end result's supposed to be because I have worked it out many times in the past. But I'm just going with my gut here. But I can see it is going to work out. So, okay. Now what I'll do is I'm gonna do some rearranging here. Okay. I'm going to take the terms involving n and group them together. So it's nxk minus x. Okay. And I still have this mx over here. Okay. Now, and now what I'll do is I'll distribute the m inverse through what's in parentheses here. So that's going to give me m inverse n times xk minus x. And then I have m inverse mx, the m inverse and the m cancel, so that gives me x, minus x. So those are gone. But I have xk minus x. That's ek. So I'll just summarize this relationship here. This is definitely worth boxing. Ek plus 1 is equal to m inverse n times ek. So that is how the error changes from one iteration to the next. So you want to make sure that you choose your m and n in such a way that this multiplying a vector by this matrix will cause the vector to get smaller. And so with each iteration, the error will converge towards 0. Now, there's a couple conditions I can give you for this working out correctly. What I can do is I can take norms of both sides, vector norms. Doesn't matter which norm. So I can say ek plus 1, the norm of it, which is equal to the norm of m inverse n ek. But now I can use the property that the norm of a product is less than or equal to product of the norms. So now we have a matrix norm of m inverse n. Okay. So, what do I need to be true of m inverse n, the norm of it, to make sure that the error goes to 0? What? Okay. All right. So, what property? Because norm of m inverse n, that's just a number. So here I have the size of the old error, the size of a new error. I need the size of the error to go to 0.
Oh, m needs to be it needs to be less than 1.
Yeah. So if it is less than 1, then this will work. So we could say, all right. Well, this is a sufficient condition. Well, first, any questions about the manipulations up to this point? What?
No question.
Okay. And if you need time to catch up running, just let me know. I definitely do not begrudge that.
Hey, I just want to make sure that's supposed to be a T and an L, right?
Wait, where?
Oh,
Tall.
Yeah,
TLL.
yeah, tall for tolerance. Yeah.
But my guess of the tolerance is mostly going to be EPS.
Oh, well, for toy problems, yes, but well, actually, that could be a bit much to ask for, just because of round-off error.
Yeah.
And also depends on how ill-conditioned the matrix is. Okay, so a sufficient condition is that so the error after oops, I didn't write it that way before. So the error goes to 0 if the norm, some norm of m inverse n is less than 1. Okay. Now, I say for some matrix norm because you may have a situation where, for instance, the infinity norm is less than 1, but maybe the 2 norm is not. But if you can find one matrix norm, any of them, in which this is less than 1, that's good enough. Okay, so that's our sufficient condition. However, it's not necessary. There are matrices for which any matrix norm you can find is greater than or equal to 1, and the error still goes to 0. So I say it's sufficient, but not necessary. So this is not an if and only if deal. Now I will give you an if and only if deal. So the error goes to 0, that's 0 vector, if and only if this quantity, rho of m inverse n, which I need to define, this is called the spectral radius of m inverse n. Now, what is the spectral radius? So for any matrix A, the spectral radius of A is equal to it's the largest magnitude or absolute value of any eigenvalue of A. So we're taking the absolute value of all the eigenvalues of A, which can be real or complex, and whichever one is the largest, that gives you the spectral radius. So that must be true, or there's no hope. Your iteration will not converge. Now, it may happen where, depending on your B from your AX equals B system, you might get lucky, and it still works out. But if this does hold, then it doesn't matter what B is, and it doesn't matter what your initial guess is either. It will converge.
It says lambda would.
Oh, there's a subscript, lambda sub I. So any matrix has n eigenvalues, and we just label them lambda 1 of A, lambda 2 of A, and so forth. Okay. Often it's easier to show this condition is true, that you can find some norm for which it works. But I want to make you aware of the most stringent condition for convergence. Because it turns out the spectral radius of any matrix is always less than or equal to any norm of the matrix. So that's why this works, that you can have situations where this is greater than or equal to 1, but this is still less than 1. Okay. Yes?
And that's any P norm.
Actually, it's any induced norm. Any matrix norm that is induced by a vector norm. Like where you take the max over.
Okay, yes.
Yeah. Now, so in other words, this that would not include the Frobenius norm, except the Frobenius norm is always greater than or equal to the 2 norm. So in effect, it is covered.
That is rho, right? Or is it a P?
That's the Greek letter rho.
It is rho. Okay, because
Yeah.
he said P, which really threw me off. I was like, I swear that's rho.
Oh, okay.
No, I was referring to a P norm.
Oh,
I just,
yeah,
I
yeah,
turned
There's,
P.
there's no P on the board.
That's what I thought.
Yeah, yeah, yeah. He was talking about something else. Oh, password me. I didn't catch it in time. Okay. Thank you. Okay.
There's gonna be a bunch of YouTube videos and be like very awkward.
Okay.
I'm gonna start sticking my tongue.
All right. So now, okay. So now I can finally talk about a specific stationary iterative method. In other words, we'll actually pick out a M and N. Now there are only 3 particular stationary iterative methods that I'll cover. I may not get to all of them today, but it's okay. But they're all quite similar to each other. So I'm going to decompose A into a sum. D plus L plus U. So D is the diagonal, and then L is strictly lower triangular, and U is strictly upper triangular. So in other words, if your A is, all your entries are in here, so you take a main diagonal, that is your D. Everything strictly below the diagonal is L, and everything strictly above the main diagonal is U. So here we have all the entries A, I. This is A, I, J for I strictly greater than J, and this is A, I, J, I strictly less than J. So we break the matrix down to those 3 parts, because then that makes it a lot easier to describe these iterative methods. Because I gave a criteria earlier that if you write A as splitting M minus N, you're going to be solving systems involving M. So those systems need to be easy to solve. So for first method, okay, so first method is called the Jacobi method. So for that one, I will set M equal to D, so just the diagonal. So that is a very easy system to solve. And then N would be everything else. But since A is equal to M minus N, I need to throw a minus in here. So that way, M minus N is equal to D plus L plus U, which equals A. So now, I'll write the iteration in 2 different ways. First, in matrix vector form. So we're solving a system at every iteration. D times xk plus 1 is equal to B minus L plus U xk. So this is the matrix vector form of a Jacobi method. And it's based on what I have written here in the algorithm, where I just set M equal to D, and then N is equal to minus L plus U. All right. So what you could do is you could code this up in MATLAB, where like this line here, because you can say like your new x is equal to D backslash all this, where you plug in your old iterate. But what I'm going to do now is I'm going to write this out component by component. Because now certainly I can do this, xk plus 1 is equal to d inverse but since D is a diagonal matrix, D just consists of A11, A22, A and N, zeros everywhere else. Okay. So that means that D inverse, you just take reciprocals of those. So none of them had better be 0, or you couldn't use this method, unfortunately. Okay. All right. So if I write out this iteration in one component at a time, I'll have the following: that x I k plus 1. So this is the ith component of a vector xk plus 1 is equal to the ith diagonal entry of a D inverse, which is 1 over aii, times the ith element of this. So that's going to be, well, bi. And then I have minus, and I'm going to break this up into two sums. So I have here, L consists of lower triangular entries. Oops, I don't want that there. So I need to fill in the rest here. So this sum will correspond to j less than I, and this corresponds to j greater than I. So this is LXK, or minus LXK. This is minus U xk. Because when I is less than j, that's upper triangular. When I is greater than j, that's lower triangular. Okay. Now, where this came from is a formula, which is something really you need to have fresh in your mind. The formula for matrix vector multiplication. So if y is equal to a times x, that means that yi is the sum of aij xj. So notice how the column index of a matrix entry is the same as the index of the element of a vector x. So those keep increasing. The first index is I that matches this. So what we have here is a matrix vector product. Notice again, these two indices change together, and same thing over here. All right, so these two are equivalent. You just have one written in matrix vector form, the other is written in component form. So some might find this easier as for a coding perspective. So you have a for loop. So this goes from I equals 1 up to n. So you'd have a loop, I going from 1 to n. And in that loop, you do this. Now, for these sums, you would also have loops. Like j going from 1 to I minus 1, or j going from I plus 1 to n. You've seen these kind of loops already, forward and back substitution. Okay, so this is the Jacobi method. Now, I'll talk later about like when we can expect this to converge. It's one of the simpler iterations. It's not necessarily the best one. But what I'm going to do is I'm going to point out one you can think of it as a flaw in it, or an inefficiency in it, and then we'll fix it, which will give us to another method. Because suppose I'm computing all of these components of a new iterate in order. So for I going from 1 to n in sequence. Well, here, suppose I'm let's let I equal to 5, for example. I'm computing a fifth component. I've already computed the first 4 components of this vector. This is my new iterate. When I get over here, I'm counting j equals like 1, 2, 3, 4. And I'm using those 4 components of the old iterate. When I've already computed the first 4 components of the new iterate, and I'm not using them. Seems kind of silly. Why not use the most up-to-date information available about what you're computing? Because we're all getting closer and closer to the exact values anyway. So what I could do is, so what's happening here is, the portion of this minus LXK uses out-of-date information. It's because L is strictly lower triangular, it's using all components of xk before component I. So what I can do is I can tweak this iterative method to use xk plus 1 rather than xk.
That's a minus sign? Or
Yes.
just a, okay.
Yeah, just because it's being subtracted in the original. Well, minus sign is not really an important part of this. But.
Okay.
Okay, so now if we use up-to-date information, then I have xik plus 1, so only a very slight change. It's equal to 1 over aii, bi minus, so for this sum, I have aij xk plus 1 j. And then for the other sum, that has to stay the same because these components of xk plus 1 I have not yet computed. So I still have to use the old. Okay. Now, this is called the, actually, I won't give a name yet. So this is in component form. Now I'm going to write this in matrix vector form. So I can say xk plus 1 is equal to d inverse times b. So now what I have here, I'm multiplying still by minus L. So I have minus L, but now it's xk plus 1 rather than xk. And then I have minus u xk. So really what I should do is I should take that xk plus 1 term and move it to the other side. So what I'll do is I'll multiply both sides by d. So now I have d, and then this goes to the other side. So now I have d plus L xk plus 1 is equal to b minus u xk. So this is my iteration now in matrix vector form, contrasting with what I have over there for the Jacobi method. This is method 2 that we're talking about. It's a whole new method now. It's not just a modification of Jacobi. Or in other words, we don't call it Jacobi anymore. So in other words, m is equal to L plus d, and n is equal to minus u. In other words, we've taken the L and moved it over from n to m. And So this method is called the Gauss-Seidel method. I'm hoping that Gauss actually played a role in this method's development, unlike Gaussian elimination. I mean, he did do a lot of things. They're named after him, but okay. So now we have this new iterative method. It often is more effective, in other words, converges more rapidly than Jacobi. Not always. It's not so clear cut. Okay.
On your top one, is that 1/8
Yes. Yeah. So D plus L, that is a lower triangular matrix. So this system is still easy to solve. It's forward substitution. But so really, it's almost like that's what's being carried out over here. And then in forward substitution, you're dividing by diagonal entries. That's what's happening over here. Okay. Now, so I want to give, I won't have time to cover a third method, but so a comparison of the two. So the point in favor of Gauss-Seidel is that Gauss-Seidel, which I'll abbreviate GS, generally converges faster due to its use of newer information about X. In some cases, it can converge a lot faster. There are some examples where, because I said the spectral radius of m inverse n has to be less than 1, or we like to have the norm of m inverse n less than 1. The smaller it is, the more rapid convergence will be. There are some examples where the spectral radius for Gauss-Seidel is the square of the spectral radius for Jacobi. So if I let t, please don't do too much packing up yet, I do have 5 more minutes. If I let t equal m inverse n, that's my iteration matrix. We want the norm of t to be as small as possible. So sometimes the spectral radius of t for Gauss-Seidel is equal to the spectral radius of Jacobi, which I'll label tj, squared. What happens when you square a number that is less than 1?
You get smaller.
Yeah. So that will cause convergence to be a lot more rapid. I've seen some examples of it. Again, it's not always true. So that's the point in favor of Gauss-Seidel. The point in favor of Jacobi is parallelizable. And what I mean by that is all the components in Jacobi, all the components of x k plus 1 are computed independently of each other. So if your computer can do parallel processing, you can take advantage of that. Gauss-Seidel cannot. Gauss-Seidel, you cannot compute this component until all the ones preceding it are computed because you're relying on them. So whereas Jacobi doesn't have to wait. So that's significant. That's one reason why some people still use Jacobi if you have a parallel architecture that can offset this advantage of Gauss-Seidel. So this is what happens when we see all these numerical methods. Rarely are there clear-cut winners, or if there are clear-cut winners, it's only on a very narrow category of problems, which I exploit all the time in my research. So it's important to keep in mind that there are advantages and disadvantages to both, which can make method selection difficult, but that means knowing more about your specific application. Okay, so in the last few minutes, let's see if you've absorbed anything. Why are we even talking about this when we have all these methods, Gaussian elimination or Cholesky factorization, all the direct methods? Why do we even have iterative methods? Why are they valuable to talk about?
There's 4 reasons.
Give me any of them.
Oh, well, if you have an approximation,
Yeah,
if you don't have an A,
yeah,
if, I'm flipping,
A spares.
We
So
don't need
close.
high
yeah.
accuracy.
you don't need
It's
high
what?
accuracy, and the fill-in thing. Sparse.
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 Yeah. Okay.
Sparse.
All right.
Yeah,
Well,
it is.
if I
Spells the same.
if I had gold stars, I'd be giving them out. Okay.
Sparse with a
All right. But an iterative method doesn't always work. But when does it work? When does when does a stationary iterative method definitely converge?
Oh, when
If that's
if
not.
the spectral radius.
Yeah, spectral radius of m inverse n for your choice of m and n is less than 1. Okay, now, all right, so I'll definitely have to continue with this on Tuesday because there's one more method to cover. That's the best of them all, and other properties. So,
Question, or what else off the video?
okay, all right, and yeah, of course I'll stick around if anybody has any homework questions or anything like that.
Is that 2 a -2 or a positive?
That? Oh,
Yeah.
that's a smudge.
Okay.
Yeah, that's a square. Yeah, yeah, it's to the -2. That'd be really bad. Okay. Okay.
My question for you